Okay, so let's look at a couple additional examples of performing a hypothesis test all the way through. And we're going to perform this using the exact same steps that you're going to have given to you on the tests or final. So these steps I've given you, the first page kind of just summarizes all of the steps using both methods, so using p-values and critical regions. You're going to be expected on the final exam to solve this using both methods. So you need to be comfortable using both the p-values and the critical region method. So let's look at a couple of examples. So for this first example, sunspots have been observed for many centuries. Records of sunspots from ancient Persian and Chinese astronomers go back thousands of years. Some archaeologists think sunspot activity may somehow be related to prolonged periods of drought in the southwestern United States. So let x be a random variable representing the average number of sunspots observed in a 4-week period. A random sample of 40 such periods from Spanish colonial times had a sample mean of x bars approximately 47. Previous studies of sunspot activity during this period indicate that sigma is 35. It is thought that for thousands of years, the mean number of sunspots per 4-week period was about mu equaling 41. Sunspot activity above this level may or may not be linked to gradual climate change. So what we actually want to test is, does the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41? And we're going to use a 5% level of significance to test this claim. So the way these steps are broken down, I'm going to give this to you in this exact same layout. So if you look in the Moodle course, we already have these steps laid out on a blank page for you to use as you're practicing the homework. I would encourage you practice using these steps because it's going to be laid out exactly like this. So the first thing we want to do is state our two hypotheses, the null hypothesis and the alternative hypothesis, and identify alpha. So to find our hypotheses, we want to look at what we're being asked. So does the data indicate that the mean sunspot activity was higher than 41? So our claim here, and remember it's usually going to be easiest to start with what your claim is. So the claim is the mean activity was higher, so greater than 41. So because of that, we know, since this does not have equality, that is going to be our alternative hypothesis. So our alternative hypothesis is mu is greater than 41. And we still want to identify this, even though I've already done it. We want to identify that as our claim. So now we know our null hypothesis is always going to be mu equals some value. Or if you were testing another parameter, that parameter equal to some value. So here we're going to test the null hypothesis. Mu is the same number, so mu equals 41. And then alpha, remember alpha is just another way of saying what is your level of significance. In this case, we want to test it at the 5% significance level. So alpha is 0.05. Even though I will give you alpha in the question, you still have to tell me alpha. This is probably one of the biggest things I see students forget to do, and it's one of the easiest points you can get. So make sure you're specifying what alpha is when I ask for it. So the next part, what type of test will you conduct? So remember, if I say the type of test, I mean, are we looking at a left-tailed test, a right-tailed test, or a two-tailed test? So remember, to figure out which type of test you're going to conduct, you want to look at your alternative hypothesis. The alternative hypothesis tells you the type of test. So in this case, if we look at our alternative hypothesis here is mu is greater than 41. So because that inequality points to the right, we know we're going to do a right-tailed test. So this is the exact same as if you were thinking, what's the probability that x bar is greater than some value? or the probability that x bar were less than some value. So whatever that inequality, whatever way it points, remember in chapter 6 it told you which way to shade. It's doing the same thing here. It's telling you which side we're interested in. When we get down to critical regions, you're going to see our shading is going to look exactly like the shading you're used to doing. Alright, so the sample test statistic, that means are we going to find a z-score or a t-score? So remember, the criteria for using z is you know the population standard deviation sigma. The criteria for t, you do not. You have the sample standard deviation s. So in this case, if we look back at the information we're given, we're indicated that sigma is 35. So here we're going to use z because we know sigma. But don't forget, we also have to make sure that we're taking the criteria for central limit theorem into account because we are using central limit theorem here. So we still have to also determine whether or not central limit theorem applies. So is n greater than or equal to 30, or is the population normally distributed? So if we're looking back at the information we're given, we don't know anything at all about the shape of that original population distribution. But we do know that our random sample had 40 such periods. So n is 40, which is definitely greater than or equal to 30. So that's our justification for why we can use our t-test, or sorry, our z-test. So now let's calculate our z-statistic. So remember, this is just going to be the same as the z-score formula from chapter 7. So z is the sample mean minus the population mean divided by sigma over square root of n. So then our sample mean is given to us as 47 minus our population mean, which is given to us in our alternative hypothesis. So, our null hypothesis. If you look at your null hypothesis, it is going to tell you what to let mu equal. So we're going to assume mu is 41, because remember, we always assume at the beginning of a test that the null hypothesis is true. So this is going to be 47 minus 41 divided by our population standard deviation of 35 over the square root of n, where n in this case was 40. So if we do that calculation, that gives us approximately 1.08 to 2 decimal places for our z-score. So now we want to find our p-value, or the interval containing the p-value. If you're doing a z-test, you will always, always, always end up with just a p-value. If you're using a t-test, most of the time, if you're using the table, you are going to end up with an interval containing the p-value. Now, it's possible if you're doing a t-test, you could end up with just a single p-value. If you're using technology, it's not going to be a problem. You'll always end up with a p-value. But most of the time, most likely, if you're doing a t-test, you're going to end up with an interval containing a p-value. But since we're doing the z-test, then we don't have to worry about that. We're going to just end up with a p-value. So remember, to find this p-value, you're really looking for the probability or the area to the right of your z-test statistic. How did we know it's right? Because we're doing a right-tailed test. So we're looking for the area to the right of z equaling 1.08 on our normal table. So remember, if we do that on our normal table, we're going to look up 1.08. So there's our 1.0, our 0.08, find where they intersect. So our number on the table is 0.8599. So because we want area to the right, it's going to be 1 minus that number. So 1 minus 0.8599. And so if we calculate that, that is 0.1401. So our p-value in this case is 0.1401. So now we want to conclude our test. So when I say conclude the test, do we reject the null or do we fail to reject the null? So remember, to determine that, you just want to compare your p-value with our alpha value. So in this case, our p-value is 0.1401 and our alpha value was 0.05. So in this case, our p-value is definitely greater than our alpha value. And so remember the criteria. If p is greater than alpha, that means we don't have enough information to sway us to reject the null hypothesis. So in this case, we fail to reject the null. And the nice thing is, our justification is literally because our p-value, which is 0.1401, is greater than alpha equaling 0.05. So the way you're justifying it is what you have to do to decide in the first place. So now we want to interpret this in context. So in other words, we want to take what we just said, that we fail to reject the null at the 5% significance level, and we want to put that back in the context of the problem. So we want to put this math that we just did back into words. So the easy way of doing that, there either is or is not in this case, and it always ties back to your claim. So our claim was the alternative hypothesis. Now we said we're failing to reject the null, which means we can't support that alternative hypothesis, right? So there is not enough evidence to support the claim that, and so then what were we claiming? So our claim was our alternative hypothesis. And so that was that mu is greater than 41, but putting that back in words of what we were asked, right? So going back to the part I underlined up here, did the data indicate that the mean sunspot activity in the Spanish colonial period was higher than 41? So that was our claim we were testing. That was our alternative hypothesis. So we do not have enough evidence to support the claim that the mean sunspot activity during the Spanish colonial period was higher than 41. And then you always want to include the significance level that you tested it at. So for example, if I tested this at the 20% significance level, we would have a different outcome, right? So you've got to know what level of significance you were testing this against. So what was your barrier to cut it off? So we want to include that and say at the 5% significance level. So that's all you have to do to interpret it in context. Take the math that you just said, tie it back with your claim, and basically answer the question you were asked in the beginning. So that's using our p-value method. So for critical regions, most everything we've done still applies. So steps A, steps B, steps C still apply for critical regions. The part that's going to be different is how we conclude the test. So using the critical region, we're asked to find our critical values. So that is always going to be, if we go back to our tables, if you go to the very last page of these tables, I gave you a different set. So this is also on the bottom of your standard normal table, the critical values of Z, because we're doing a Z test. I don't like this table that your book gives you as much. It's just a little bit more difficult to understand and interpret. I like the way this other table lays it out a little bit better. But again, notice it tells you this is for z-test. So it says critical value z0 in this case. So all you have to do to use this table is you find your alpha level. So our alpha in this case was the 5% significance level, so 0.05. And then find the type of test you're doing. So we're doing a right-tailed test. So our critical value is 1.645. If you're doing a left-tailed test, you're always going to end up with a negative critical value. If you're doing a right-tailed test, or I shouldn't say always, but the majority of the time, so left-tailed test will usually be a negative number for the critical value. Right-tailed test will usually be a positive number, and a two-tailed test is going to usually be both positive and negative number. So in this case, we're doing a right-tailed test. We end up with a positive number. So now we want to conclude our test again. So usually what I recommend doing is do a sketch. It's going to look very similar to the ones we've been doing all semester since we started normal distributions. So we're graphing our z-statistic and our critical value basically. So I want to start out, when you're doing this, just throw your critical value on here. So in this case, our critical value is 1.645. So we're somewhere about here. That's our critical value. And then you're going to shade the side that corresponds to the type of test you're doing. So in this case, we're doing a right-tailed test. So I'm going to shade my right-hand region, my right-hand tail. And so the part that I've shaded, everything to the right of my critical value, that becomes my rejection region. So everything that's inside there, if my test statistic were in there, that would mean I would reject the null hypothesis. Everything that's not shaded is our fail to reject region. So if our test statistic is in that side, then we don't have enough evidence. We fail to reject the null. So if we go back and look, our test statistic is 1.08. So we just put it on the number line where it would be. So 1.08 is going to be somewhere right about here. So because z equaling 1.08 lies in our fail to reject region, we fail to reject the null. That's how we conclude our test. So we fail to reject the null, and the y, since z equaling 1.08, lies in the rejection region, or in the fail to reject region. That's all you need for your y. The sketch really does explain your reasoning why.